Often when we are modeling with differential equations, we want to incorporate components of rate of change that switch on or off at particular times. One example of that would be an electrical circuit where perhaps the battery is disconnected and then at some moment the battery is connected, and then things start happening within the circuit. Laplace transforms allow for us to incorporate discontinuous functions with relative ease, and that's what we're going to talk about in this video. Often called the Heaviside function or the discontinuous function, it allows us to do precisely that, switch things on or off. So let's go ahead and define the most basic version of the discontinuous function, called the Heaviside function, named after Heaviside. You can go look up more about him if you would like. Alright, so we're going to define this function called u, because his name is Heaviside, so of course we're going to call it u. I don't know why we call it u, but that's just the standard template. And it's u sub a of t. Okay, so it's a function of time. Forget about differential equations right now. Let's just focus on what this means. It's a piecewise function that's defined as either being 0 or 1. Off or on. So it's off for all times before a. Notice that the subscript here is a. That denotes the time at which the switch then turns to 1. So if t reaches a or is greater than time a, that output becomes a 1. So let's take a quick look at a graph of what this function actually is telling us. So here we have time, and this will be our u sub a of time. Okay, and so let's just say there's some time here. We'll just say right there, that's time equals a. And up until that point, our function is defined to be 0. Okay, so just drawing a horizontal line, it's off. And then I'm going to put an open circle here because it's not 0 at time a, it's just 0 before time a. And then at time a, well, now the function goes to 1. Okay, so I'll put a solid dot at 1, vertical position of 1, and it remains there for all time thereafter. Okay, now, usually we're not concerned about time less than 0, because usually it is time that we're keeping track of, but now the switch turns on. Okay, that's all this function is. So if a was equal to, say, if this was sub 2, then this would be time 2 at which this change would take place. Okay, so there are some pretty cool things we can actually do with this. Why would we just want something that's either a 0 or a 1? Well, we could really take advantage of this, and I'll just show one possible interesting variant of this. Okay, and so let's say there's our graph again. What we'll do is now take some function. Okay, so I'm going to pick the function e to the t minus 3. So that's an exponentially decaying function. And relative to e to the t, if you recall, this is actually shifted 3 units to the right. So e to the t at t equals 0 would have a y value of 1, would have an output value of 1, but we actually don't want it to, we want to shift it over 3 units. So here's e to the t, right? There's 1, and e to the t is going to, oops, opposite direction. I wanted to do e to the negative t minus 3. Let's do that. E to the negative t versus time would be an exponentially decaying function. Now, e to the negative t minus 3 would be an exponentially decaying function that actually you can think of as being shifted over 3 units. So there's 1, and the function actually just gets shifted to this point, and then from there it decays down. Okay, and so that's exactly the same function, just shifted over to the right 3 units. Okay, let's take a look at that. If I take the function e to the negative t minus 3, and I multiply it by u sub 3 of t, then I'm basically saying let's take the exponential function and multiply it by either a 0 or a 1. Now this is a piecewise function because of the Heaviside in there, so let's think about what this will be. If time is less than 3, or subscript, then u will take on the value of 0. So it will be e to the negative t minus 3 times a 0. Well, you can imagine that what that's going to do is it is going to zero out that entire quantity. Okay, so basically, before time 3, nothing is happening. The signal that we have, 1, 2, 3, is just going to be a constant 0. There's nothing going to be going on. Again, open circle here at time 3. And then I'll just say that this is y equals, so this is the y-axis. Then at time 3 and beyond, u sub 3 of t will equal 1, okay, and 1 times e to the negative quantity t minus 3 is e to the negative t minus 3. So basically it's as if we switched on our exponential function, but we don't actually want it to start until time 3, and then it begins decaying. So we took a 0, 1 function, and by multiplying the 0, 1 function by a non-constant function, we can actually have it do some pretty interesting things. Now you can also just scale u sub a. You could multiply it by 5 and make it jump from a 0 to a 5 instead. Here's one more cool thing you can do with it. And let's just say I take 2 Heavisides and I subtract them. So I'm just going to pick u sub 3 of t minus u sub 2 of t. Now this is actually going to be a piecewise function with 3 components because at time 2 something happens and at time 3 something happens. And specifically, we know that before time 2, well, both of these are going to be 0 because for u3, nothing happens until time 3. That is, it's 0 until time 3. So this is going to be 0. Before time 2, this is going to be 0. And so, as a result, 0 minus 0 will be 0 before time 2. Now, I also need to consider between time 2 and time 3 because at time 2, this Heaviside activates, but u sub 3 doesn't do anything yet. It still remains, it remains 0. You know what? I think I'm going to subtract these in opposite order, though. Let me do this. Let me subtract them in opposite order. So I'll do u sub 2 of t minus u sub 3 of t. That won't change our 0 there. Okay, at time 2, so I'm going to say between time 2, including time 2, but before time 3, u2 jumps to a 1, u3 is still a 0, and 1 minus 0 is 1. Okay, so we have a 1 between time 2 and 3. Okay, nothing super fascinating there, but let's see what happens at time 3. What's the effect of this u3 in there? Okay, so for t greater than or equal to 3, remember that u2 is still a 1 because it's always a 1 at and after time 2. And now at time 3, u3 activates, becomes a 1, And so 1 minus 1 is 0. So notice what we did. We were able to switch on, make a switch turn on at time 2, and then only have it on for 1 unit of time, and then switch off at time 3. We could have done u2 minus u5. We could have had a 3 time unit interval where the function remains on. And so when we visualize this, you can kind of imagine there'll be just this short blip of this being on. Okay, I'll just call this y, so I can just label my axis y versus time. So time 1, time 2. Then we'll just say, maybe we'll space these out a little bit more. 1, 2, 3. Okay, so up until time 1, we're at a 0. At time 1, we jump to, oh, sorry, this is between 2 and a 3. Try that again. Okay, between, up until time 2, nothing happens. Then we jump to an output of a 1. We remain there until time 3. Now remember, at time 3, we jump back down to a 0 and remain there forever from there on out. So it's like we turned on the switch for a second and then turned it back off. So we can get as creative as we want with these. But before we do that, let's try to figure out how these are going to be handy with Laplace transforms. So if we take the Laplace of a Heaviside, we're going to argue that that result will be e to the negative as over s, where a is the time at which your function switches from a 0 to a 1. Just to show how actually simple this is, and one thing I want you to notice is we go from something that's discontinuous to something that's perfectly continuous in the S domain. So by definition, the Laplace of a Heaviside function, or any function, is the integral from 0 to infinity of the function u sub a multiplied by e to the negative st dt. Well, let's think about this. U sub a will take on one of two values. From 0 to a, from time 0 to time a, the Heaviside is at 0. So we have to integrate from 0, right, from here to here. We're going to integrate 0 times e to the negative st, because that's the value of u. But then I also have to go from a to infinity, that's here forever, plus the integral from a to infinity of 1 times e to the negative st dt. So you can see why this integral is still continuous. This is going to be 0, right? That's the area under the 0 curve, between the 0 curve and the horizontal axis is 0. And now you can compute the integral of this. I'm just going to do this in my head. It's 1 over negative s e to the negative st, evaluated at t equals a and t equals infinity. Okay. Now, I know some people will say you can't plug in t equals infinity. That's okay. We'll get the same idea. So we have negative 1 over s e to the negative s times infinity. Okay. Point here is that for negative exponents, e to the negative infinity will go to 0. Now we have minus negative 1 over s e to the negative s times a. Okay, that's going to be a positive 1 over s e to the negative, and s times a is the same thing as a times s. And so we get, if we compact this into a fraction, e to the negative as over s. So simple as that. It's a nice thing to work with. You never actually have to work with the pieces of the Heaviside function, which is pretty incredible. We'll do one more thing, and then we'll derive one more useful transform. And, well, actually, rather than derive it, I'll just show you how it works, because it is kind of a little bit of weird substitute-y type stuff. So I'll just show you why we need this one. We'll stop the video. We'll continue on with an example in the next video. All right. Here, well, what do we have going on? we have the Heaviside multiplied by f of t minus a. Well, what does that mean? Well, it turns out we already demonstrated this with our exponential function right over here, right? So we were trying to switch on the exponentially decaying function e to the negative t, but we wanted to shift it over 3 units because we kind of wanted to pretend like t equals 3 was actually our vertical axis, that at t equals 3 that's where our vertical axis is. But our vertical axis is actually back here at time 0. We just wanted nothing to be happening until time 3, and then for that exponentially decaying function to begin. So look at these two pictures here and here. It's the same function, one's just shifted over 3 units. This is very just common practice. You don't actually want the function to switch on at time 3 without shifting it, because e to the negative t at time 3, notice it's lower than it was back at t equals 0. But a lot of times we want that time 0 position to just actually start at time 3. And that's exactly what we're doing when we're shifting the function to the right. So this says, okay, first of all, notice the a there and the a there. F of t is going to be some function, right? Let's just say, I'm just going to make one up here. Let's say f of t is that. And then f of t minus a, assuming a is going to be a positive value, assuming a is a positive value, f of t minus a will be the same thing, but shifted to the right a units, right? So it starts exactly at that same y value, except a units later. And the Laplace transform of that is actually kind of weird. It's e to the negative as, and then it's another Laplace of f of t. That's kind of weird. All right, let me show you how this works, and then we'll stop the video. So let's just say we wanted to have the Laplace of u, okay, over here we had u sub 3 of t times the exponential e to the negative t minus 3. Okay, so the first thing you need to identify is what is the function? What is the unshifted version of that function? Well, clearly, this right here is our f of t minus a. Notice that it's shifted over 3 units to the right. So that means if I hadn't shifted it, I could conclude that f of t would just be the exponentially decaying function. So it's kind of like we're taking t minus 3 and replacing it with just t, right? So where f of t minus 3 means plug in t minus 3, f of t means replace t minus 3 with just t. Okay, and then our value of a, which should be the same here, and it should be the same here. If it's not, then this isn't going to work. A is equal to a 3-unit shift. Once you have those two pieces, the Laplace will equal e to the negative as, so e to the negative 3s, times the Laplace of e to the negative t. Okay, the reason we have to write it like this is because that function may be exponential, it may be sinusoidal, it may be whatever. So we don't actually know what its Laplace is until we know what that root function is. And so now I know that e to the negative a, or e to the at will be, its Laplace will be 1 over s minus a. So 1 over s minus, this is a negative 1 here, so minus negative 1, which is, of course, s plus 1. And there is our Laplace transform. So you can write it as e to the negative 3s over s plus 1. Just as a key point, when you're working backwards, you're inverting. If you see the e to the negative as in there, and there's something else that it's being divided by or multiplied by, inevitably that's going to mean you want to work backwards. So if I saw this, I saw e to the negative 3s. First of all, that would tell me my a is 3. And then 1 over, actually, I should probably look at this one. 1 over s plus 1. Oh, hey, that's e to the negative t. So that would identify my f of t. And then to get the original thing that was Laplace to get it, I know that it's the Heaviside base 3. And then shifted over e to the negative t, shifted to the right 3 units, so t minus 3. So working backwards is a little bit more challenging, but as long as you kind of follow the logic of it, it's very, very structural, very procedural. In the next video, we'll just take a look at a really cool example of how we can administer drugs to patients over time and see when we should stop infusion.